Jai Hind everyone. I am Vikas Rathi, working in Ajay Kumar Garg Engineering College as an assistant professor. Today I am going to discuss about the engineering physics, okay, because this is the name of the subject which I am going to discuss today, engineering physics, and the code is KAS 101T or 201T. Basically in our semester the subject code is KAS 101T and in even semester it is 201T. So T here represents for theory. Now the topic which I am going to discuss, this is relativistic mechanics, and in relativistic mechanics basically I will focus today only on length contraction and time dilation. References for this topic, mainly Concepts of Modern Physics by Arthur Weiser, and this is the main textbook which is the main textbook which I have discussed for this topic. Other references are Engineering Physics, this is Theory and Practical by Katiyar and Pandey, Applied Physics for Engineers by Neeraj Mehta, Engineering Physics by Malik and A.K. Singh. Next one is Engineering Physics by S.K. Gupta and Engineering Physics by S.L. Gupta. But the main textbook for this topic is Arthur Weiser. So this is the textbook which is best for this topic. In this unit, basically in engineering physics we discuss following topics like introduction. In brief, today I will discuss the introduction of this basically relativistic mechanics, then frame of references, inertial non-inertial frames, Galilean transformation equations, Michelson-Morley experiment, postulates of special theory of relativity, Lorentz transformation equations and length contraction, time dilation, velocity addition theorem, variation of mass with velocity, Einstein's mass energy relation, relativistic relation between energy and momentum, massless particles. But today I will focus only these two topics, length contraction and time dilation. So I will discuss in detail about the length contraction and time dilation. So before discussing these topics, length contraction and time dilation, I will give a brief introduction of special theory of relativity, what is special theory of relativity and its types, category of the special theory of relativity. Basically in special theory of relativity, we discuss about the relative motion between two object and observer. And this theory can be divided into two categories. Special theory of relativity, which is in short form it is known as STR, and this is proposed by Einstein. So this is also known as Einstein's theory of relativistic mechanics. In special theory of relativistic mechanics, basically we will deal with the relative motion between object and observer. Okay, the motion will be in this type, in this theory, motion will be relative, but it will be in a straight line, okay, and the velocity will be uniform, it will be constant. That means the motion will be in a particular direction only, okay, it will not be in multi direction, and the speed will remains uniform, okay. And this is also important condition that here the speed will tends to the speed of light, okay. Then the second category, second type of theory, this is general theory of relativity, also known as GTR. In GTR basically again we will discuss the relative motion between object and observer, but here the motion that will be arbitrary motion. That means the motion between object and observer may be in any direction, and second one is the system means here object and observer, they may be in accelerated form. That means the velocity between them, it will not be uniform, it will vary with respect to time, right. Then before we are going to discuss this topic, always we will consider two frame of references, one will be stationary, another one will be a moving frame, okay. So we must know about what are the frame of reference or what is the frame of reference and its type. Basically to explain any phenomena in relativistic mechanics, we will consider frame of references. What is a frame of reference? Basically it's a coordinate system with respect to which we measure the position of any object or any event. Okay, so we have to consider a coordinate system which is known as frame of reference. So I will not go in detail of this frame of reference. So just I will discuss here its types of the frame of reference. Here frame of references can be divided into two categories: inertial and non-inertial. As you know, inertial frame, basically a frame of reference either at rest or moving with constant uniform velocity, that means zero acceleration, is called inertial frames. That means basically the velocity will remains uniform between object and observer here in inertial frame, or if the frame is in rest position, it will be in rest position. If it is moving with uniform velocity, then it will move with a uniform velocity. In inertial frame, all the Newton's law, they are valid. Net force will be 0. Okay, an example, you can take any example, like here a train moving with uniform velocity is a inertial frame. Similarly, non-inertial frame, a frame of reference which is either having a uniform linear acceleration or is being rotated with uniform speed. That means here the frame which is accelerated basically. Okay, so there will be no uniform motion between object and observer in non-inertial frames. So they may be in rotated form. That means the motion in non-inertial frames may be rotatory motion. Okay, Newton's law, they are not valid in non-inertial frames. Net force does not 0. And examples here, the specific examples, say freely falling elevator, okay, etc. So this is the basic about the inertial and non-inertial frames. Here to explain any phenomena, we will consider always in frames, and we will consider only inertial frames. Then in brief, I will give some about the postulates of special theory of relativity, because the whole theory of special theory of relativity based on two postulates which are known as Einstein's postulates of special theory of relativity. First one is law of equivalence. In a law of equivalence, all the laws of physics, they will all are equally applicable on in inertial frame of references. That means law of equivalence means the form of all the laws of physics that will remain same. It will not change if we go from one inertial frame to another inertial frame. It will remain same. Means here, that means if any law in one frame of reference we represent with a linear form, with a linear equation. So the form of the law that will remains linear in another frame of reference. It will not change with respect to frame of reference. So it will remains linear form. That means that law that will remains in the linear form. And if it is in quadratic form in one frame of reference, then it will remains in quadratic form with respect to another frame of reference. That means their form cannot be changed if we go from one inertial frame reference to another inertial frame of reference. Second postulate is law of constancy of speed of light, and according to this, the speed of light which is a universal constant, and it will remain same in all inertial frame of references. So it C here, C will represent the velocity of light in vacuum. So that means the velocity of light in vacuum remains same. It will be independent of frame of references. So now I will discuss length contraction, which is the main topic which I am going to discuss today. Length contraction first and time dilation. So first I will discuss length contraction. So first I will explain what is length contraction. So to understand this phenomena, length contraction, okay, we will consider two frames, two inertial frames. One is fixed frame, another one is moving frame. Fixed frame is also known as stationary frame, and I can name it S frame. And second, which is a moving frame and moving along x directions only, so I can name it this frame as a S prime frame. This is moving along x directions only. So now to understand this length contraction phenomena, basically the length of any object in a moving frame will appear contracted. It will decreased. That means if we consider two frames, one is fixed, another one is moving frame, and if we consider the object in, suppose here in moving frame and observing frame, the rest frame from the fixed frame. So then length will contracted, or vice versa. That means if we consider this object in fixed frame and observing, measuring its length from the moving frame, then again the length of the object will be contracted. Means here, if object and observer both are in same frame of reference, then the length will remain constant. Okay, or if we put this frame, this object in fixed frame, then again observer is also in the same frame, that means in the fixed frame of reference, then the length will remain same. It will not change. But if object and observer, they are in different frame of references, then length will contracted, length will appear contracted, right? We know that according to classical mechanics, all the phenomena like length contraction, length, time, masses, all are absolute. They will not depend upon the frame of reference. But in relativistic mechanics, length, time, velocity, and the mass, these all phenomena, they will depend upon the frame of references. Okay, so they will vary. Okay, some may be contracted, some may be increased, and vice versa. So that means you can say these all quantities, they vary if we measure them from another frame of reference, right? So to find out how much the length of the object will contracted, the amount of the length which will be contracted, we can measure using the Lorentz transformation equations. Okay, we already know what are the Lorentz transformation equations. So to find out the amount of the contracted length of this object, here initially we have considered this object in moving frame. So here this is suppose object AB, these are the ends point A and B, and the coordinates with respect to the moving frame, that means the observer which is in moving frame, they are suppose x1 prime and x2 prime, and the length of this object is L0. So that means here with respect to moving frame, now we can simply say the expressions for the L0, that means value of L0 will be x2 prime minus x1 prime. This is suppose equation 1. So that means the length of this object with respect to moving frame, that will be L0, and value of the L0 will be x2 prime minus x1 prime, right? So this length, because here both object and observer, they are in same frame of reference, so now the length of the object will be its actual length, right? Same time, if this object is observed from the fixed frame, then assume that the length of the same object AB with respect to the fixed frame, which is also known as stationary frame, is suppose L. The length of this same object is L with respect to fixed frame. Then the coordinates of the ends points of this object AB with respect to this fixed frame from the origin of this frame, they are suppose x1, and the another end point which is B here, suppose the coordinates, they are x2 with respect to the fixed frame. So that means the value of the L, that means length of the same object with respect to the fixed frame, which is a stationary frame, that will be x2 minus x1. So simply we can write the value of L0 and L, that means length of the same object with respect to the moving frame and the fixed frame from the another frame. Okay, so these are the expressions of L and L0 here. L0 will be the actual length of the object because we have considered this object in the moving frame, and observer initially that is also in the moving frame. Now if we change this observer in the fixed frame, that means the position of the observer in fixed frame, now the same object is observed from the fixed frame, then we have assumed that the length of the same object with respect to fixed frame is L, so value of L will be this much. Now to find out the relation between L and L0, L0 is here, as I have already told, this is the actual length, and L is the contracted length, it will be the observed length. Okay, so to find out the relation between these two lengths of actual length and the observed length, we will use here Lorentz transformation equations. We know the relation between the space and time coordinates with respect to the Lorentz transformation, and the value of the x2 and x2 prime that can be related with respect to these transformation equations. So here the value of x2 prime will be here x2 minus vt divided by root 1 minus v square upon c square. This v, this is the velocity of the moving frame along x directions with the fixed frame, with respect to the s frame. Okay, and the time, this is the time with respect to fixed frame at the end point A, that means initial point A, that means the events which are occurring at point A. So this is the time. Okay, so we can write this relation. Similarly, we can relate x1 prime coordinate and x1 in two inertial frame of references. So the value of x1 prime will be here x1 minus vt divided by root 1 minus v square upon c square. Then to find out the relation here, we can subtract equation 1, okay, from suppose we will put the value of x1 prime and x2 prime in equation 1 here. So you will find out the value of L naught will be x2 prime minus x1 prime with respect to equation 1. So if you put the value of these two x2 prime minus x1 prime, so we will find out this relation. Okay, then after simplifying this, we will have simply this expressions, and with respect to equation 2, the value of x2 minus x1 is L. Okay, so that means we have a relation between here between L and L naught, that means the observed length of the object and the actual length of the objects. So here this is L equal to L naught times root 1 minus v square upon c square. So we know that v always less than c, the velocity of light. Okay, so that means okay, so in that case, so sorry, if this will not be much less than here, this will be less than c here. So with this condition, we know that the value of L, that will be always less than L naught, that means the observed length will be less than the actual length. So that means we can conclude here that means the contracted length, that means the length will get contracted along the direction of motion by a factor root 1 minus v square upon c square. Okay, now if we take some approximations, like if v much less than c, that means the value of this factor will be approximately equal to 1. Okay, and then L will be equal to L naught. This is the condition here according to classical mechanics. That means if we discuss some phenomena like length and time, mass, velocity, we will discuss them with respect to these conditions when the velocity is much less than the velocity of light. Okay, so that means according to classical mechanics, length will remain same, length is an absolute quantity and the value will remain same, it will not depend upon the frame of references. Like, so that means L will be equal to L naught here. Now, if v tends to c, another conditions according to which we have discussed this, that means v tends to c, in that case VL always less than L naught. That means observed length will always less than actual length. So that means we can conclude here that length will always contracted. Okay, but condition, which is the primary condition, that v tends to c. So this is the time dilation phenomena. So I will conclude here about the length contraction. Length will only contracted if object and observer, they are in different frames. Okay, length will only contracted when object and observer, they are in different frame. Okay, and the velocity of the frame of reference which is moving, that tends to the velocity of light here. Okay, so there are two quantities here, L and L naught. L will be the observed length, L naught will be the this is the actual length, right? So length L naught, this is also known as proper length. So proper length means when object and observer, they are in same frame of reference, right? And observed length means when object and observer, they are in different frame of reference. Here we can consider, we can discuss this problem, this phenomena, if we consider this object here in fixed frame and observing from the moving frame, then again we will find out the same relations here. between L and L naught. So length will always contracted if object and observer, they are in different frame of references, right? Now the another phenomena which I am going to discuss today is time dilation. First I will discuss what is time dilation, right? So time dilated, as we have discussed, length is contracted, length decreased if we are measuring from the different frame. Time dilated, time increased. That means if we are measuring the time interval between the two events, okay, from the another frame of reference, then this time interval will dilated, it will increase with respect to the another frame of reference. But if we are measuring the time interval between the two same events in the same frame of references, for example, here we have considered this clock C in moving frame and measuring the time interval between the two events from the same frame, from the moving frame, then this time interval, this will remain same. That means if a observer is measuring the time interval between the two events, right, between the two events of this clock, and he will find out that the time interval with respect to him, that will remain same, okay. So it will remain same, that will be the proper time. But if we change the frame of reference of this observer, that means if we shift that observer in the fixed frame in the another frame of reference, and if he is measuring, okay, the time interval between the same two events, right, then it will dilated, it will increased, right. So if we consider object, means here clock, and the observer in the same frame, means in the moving frame, then the time interval between the same two events, it is known as proper time. But simultaneously, okay, if we are measuring the time interval between the same two events with respect to the fixed frame, then it will dilated, it will increase. So according to relativistic mechanics, time is not absolute, time is a relative quantity, it will depend upon the frame of reference, and it will dilated, it will increase. That means if we measure the time from the another frame of reference, it will be dilated, it will be increased. Now how much it will increase, how much it is dilated, we will find out again by using the Lorentz transformation equations. So here, as I have told that to find out the amount of time dilation, we have considered here a clock, here clock C in a moving frame, right. Again, the frames, they will be stationary, they will be inertial frames, okay. One will be fixed frame, another one will be moving frame. Fixed frame, okay, with respect to fixed frame, moving frame is moving along x directions, and the velocity of this frame, that means moving frame with respect to fixed frame, is suppose c here along x directions, right. Now time measure in a moving frame where the event is occurring, that means the position of the clock C with respect to moving frame is x prime, that means the position of the clock is fixed in a moving frame, right. Now if we will consider here that there are two events with respect to moving frame, one event occur at time t1, that means first event with respect to moving frame occurs at time t1, and another event occurs at time t2 prime, right. And the time interval measured with between these two events with respect to this frame, that means moving frame, is t naught. Then simply we can write value of t naught will be here t2 prime minus t1 prime, okay. So this t naught, this is the proper time here, because this is measured from the same frame of reference, that means where clock is already exist, clock is in the moving frame and observer is in the same frame. So the time interval between the two events with respect to this frame, that means with respect to moving frame, will be the proper time, okay. And the mathematically equation of this t naught will be t2 prime minus t1 prime. Now if we consider that there is another observer and observing the same events, okay, with respect to the fixed frame from the S frame, okay, stationary frame. Suppose the time measured, okay, of the first event with respect to fixed frame is T1, and second event, the time of the second event with respect to fixed frame is T2, and the time interval between these two is now here T. So that means with respect to fixed frame, value of T will be T2 minus T1. So now we can mathematically write time interval between the same two events with respect to the fixed frame with respect to the stationary frame, that will be T, and the value of T mathematically it will be T2 minus T1. Now again, to find out the relation between T naught and T, that means proper time and the observed time. This T, this will be the observed time here. Observed means here, because object and observer now means clock and observer, they are in different frame of reference. So this measured time T with respect to fixed frame, that will be the observed time. So now to find out the relation between T and T naught, that means proper time and the measured time or the observed time, again we will use Lorentz transformation equations. So we can here write the relation between T2 and T2 prime. Okay, right. So value of T2 will be T2 prime plus Vx prime by C square upon root 1 minus V square upon C square. Okay, we already know the relation between the space and time coordinates in two frames, okay, with respect to two frames. Similarly, we can write value of T1. T1 will be equal to, in terms of T1 prime, so it will be T1 prime plus Vx prime upon C square divided by root 1 minus V square upon C square. So we know the relation between T2 prime and T2, T1 prime and T1 with respect to Lorentz transformation equations, right? So now if we put the value of T1 and T2 in equation 2, so then we will find out value of T, and the value of T after simplifying this, we will find out in terms of T naught, and value of T will be here T naught divided by root 1 minus V square upon C square. That means relation between T and T naught, T will be here T naught divided by root 1 minus V square upon C square. We know that V always less than C, and with this condition you will find out that T greater than T naught. Means now the observed time, okay, that will be greater than the actual time with respect to this mathematical relation between T and T naught here. So that means time will dilated, length contracted, but time will dilated, time increased. If we are measuring the time interval between the same two events from the another frame of reference, then time will dilated, time will increased, right? So now we will find out the relation between T and T naught here. Now we can discuss this with respect to some approximations, like if V less than C, in that condition the value of this factor root 1 minus V square upon C square tends to 1, and in that case, in that situations, the value of T equal to T naught. Means if V much less than C, V much less than C means here, that means according to classical mechanics, in classical mechanics, we always consider that the velocity of object is much less than the velocity of light. So in that condition, the value of this factor that tends to 1, right? Then value of T will be equal to T naught. That means time is absolute with respect to classical mechanics. It will not depend upon the frame of references. But if we go on higher speeds, that means if V tends to C, okay, then in that case T always greater than T naught. Means measured time, observed time will be greater than the actual time right here. So time is dilated, right? So we have discussed that the time is dilated, length is contracted, but these phenomena, they will be applicable only with these conditions. First is requirement is, that means V tends to C here, velocity that should be high, of higher order, and if measuring the that means observing the events from the different frame, then only they will be relative, either they will remain same, that means they will be absolute quantity as according to classical mechanics, right? So time will dilated and length will contracted. Now I will here discuss the real time example of time dilation. Okay, here we have take this example of time dilation. Time dilation phenomena can be understood with the help of this real time example. Okay, so in this real time example we have considered this time dilation phenomena. Okay, well, this is the example which is considered by taking the example of cosmic ray particles, right, which are called mesons. Okay, basically they are created at a height of, okay, 10 kilometer from the earth. That means in atmosphere they are generally created at 10 kilometer height, right, and they can reach on earth. Okay, they can reach on earth. Okay, how they can reach on earth, we can find out, we can justify with the help of time dilation phenomena. For example, basically the speed of these particles is of the order of velocity of light, and the order of the velocity of light is 2.994 into 10 raised power 8. That means in terms of c it is 0.998 times c, and their average lifetime is 2 microsecond. That means if we take this simple formula according to classical mechanics, distance equal to velocity of light, then these mu mesons particles can travel a distance of 600 meter in its this average lifetime. That means in 2 microseconds they can only travel a distance of 600 meter. Okay, this distance they can travel here, right, but they are reaching on earth by traveling a distance of 10 kilometer. How we can justify that, how they can reach on earth by traveling a distance of 10 kilometer, right? So now it is possible only with the help of time dilation phenomena we can justify this, right? Here this time, basically this 2 microsecond time is in the mu mesons frame of reference, same frame of reference, right? So that means this will be the actual time, and if this is the actual time, then the observer which is in on earth, which is in different frame of reference, so according to that observer, the time according to time dilation phenomena, the measured time will be t equal to t naught. We know this relations, we have already find out this relation here, t equal to t naught divided by root 1 minus v square upon c square, right? So if you put the value of these t naught and velocity of light, these parameters, then the value will be here, it will be 3.17 into 10 raised power minus 5 second, right? So now if we use this time t, this will be the dilated time, right, and this is with respect to the earth. That means the observer which is on earth, which is in different frame of reference. Then the distance travel, again we will use this formula here. Now the distance travel in this dilated time is suppose d naught, then the value of d naught will be here, we will use this time now, okay, dilated time, and again we will calculate, we will find out the value of d naught, and this d naught will be approximately equal to 10 kilometer. That means we can here with the help of these examples we can say that we can explain this phenomena or the presence of the mu mesons particle on earth. So it is only possible with the help of time dilation phenomena, right? So this is a real time example, okay, so it can explain. Again I will repeat here that there are some important things here, that this 2 microsecond time, this will be the here the actual time. So remember, this is the actual time, means this is the measured in the same frame of reference, that means in the mu mesons frame of reference. So this time will be the actual time, right? So by using this time dilation phenomena, time dilation formula, we can find out the this observed time. So if we put the value, then finally you will find out this this time, this distance here. So we can prove, we can show the presence of mu mesons with the help of time dilation phenomena. So we can say कि time dilation phenomena, this is the real time effect basically, right? It is applicable in in real time phenomena also. Okay, so the existence of this phenomena, length contraction and time dilation, there are many examples, but these I want to say here that these phenomena, okay, this relativistic mechanics, there are two important conditions, that the velocity of the object and observer, that tends to the velocity of light, and second thing, it is applicable on microscopic level, that means in atomic level, right? That means it is applicable for the atomic particles like electron, proton and neutrons. So there are some approximations here, but it is a phenomena which is applicable at the atomic level, right? So today now I want to I have discussed this phenomena, and now I will discuss next topic in the next lectures, right? Thank you very much.